Our solar system, the Sun and its family of planets, has not always existed. Nearly 5 billion years ago, there was only a vast cloud of dust and gas called a nebula. This cloud had been slowly swirling for perhaps 10 billion years, held together by its own gravity. It was more than 99% hydrogen and helium, and less than 1% heavier elements. A star exploded near the cloud and pushed the gases of our nebula together. This strengthened the gravitational pull of those gases, and they began to come together even more, swirling faster and faster, growing smaller and smaller. As the nebula shrank, most of the matter gathered into the center as a huge, hot, very tightly packed ball of gas. In this heat and pressure, hydrogen atoms collided and combined with each other to form helium. This fusion released huge amounts of energy, which spread to the outer layers of the ball, causing it to glow. Away from the center of the cloud, the dust and gas were thinner. This material collected into a disk of hot gases. As the gases cooled, tiny particles began to form. Nearer the hot center, only rocky elements could become solid particles. Farther from the sun, the cooler gases could form icy particles. The larger clumps could gather more material, increase in gravity, and grow even more. Meanwhile, the energy created at the center of the sun was beginning to reach the surface and radiate into space, along with a wind of energetic particles. This radiation and solar wind began to push out the remaining dust and gas of the nebula, sweeping the solar system clean. The Sun is by far the largest member of its solar system family. It weighs about 500 times as much as everything else in the solar system put together. It is the only object large enough for its center to undergo nuclear fusion. It produces so much energy that it shines. From the innermost outward, the planets are Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. But only 3 planets fall into the area called the ecosphere. This area is neither too hot nor too cold for life to exist, as long as other conditions, such as atmosphere, are suitable for life. Venus, however, is quite close to the hot zone, and Mars is quite close to the cold zone. Only Earth, closest to the center, has the best suited temperatures for supporting life. Planets that formed quite near the Sun, like Mercury, grew very warm because of all the Sun's heat. Their gravitational pulls could not hold the hot, very light hydrogen and helium gases of the swirling material. They could only hold on to the small amount of matter that made up heavier gases, metal and rock. The nearby planets are therefore much smaller than the planets that formed farther away from the Sun. Called the rocky planets, the group consists of Mercury, Venus, Earth, and Mars. They are metal at the core, with a mantle or middle layer, and crust, the thin outer layer, made mostly of rock. Far from the Sun, the hydrogen and helium gases were cool enough for other emerging planets to hold with their gravitation. That meant they grew still larger and had even stronger gravitational pulls that could attract still more gas. Saturn, with its rings of dust and ice, is one example. These outer planets, like Jupiter in the background, grew much larger than the inner ones. Uranus and Neptune are the other 2 planets we call the gas giants. The cores of the gas giants are made of rock. Above the core is a sea made mostly of water, ammonia, and methane, and a gaseous atmosphere made up mostly of hydrogen. The farthest planet we can see is the dimmest and was the last to be discovered. This planet, Pluto, has a lopsided orbit that at one end comes even closer to the Sun than Neptune's. We have found out that Pluto is made up not of rock and not of gases, but of water and other substances frozen in the terrible cold 3.6 billion miles, 5.8 billion kilometers from our Sun. When the planets grew, some of the material on their outskirts remained separate. Most of the planets have little worlds or satellites that orbit them. All of the gas giants have at least one, even Pluto. Saturn has a number of middle-sized and small satellites, and one called Titan that is larger than the planet Mercury. Jupiter, at the lower right, has many small satellites and 4 rather large ones. Clockwise from the upper left, they are Io, Europa, Callisto, and Ganymede. The rocky planets are not so rich in satellites. Mars has 2 tiny ones. Deimos on the right is only 6 to 10 miles wide. Mercury and Venus have none at all. Our Earth has a large satellite called the Moon. It compares in size to the moons of Jupiter and Saturn. The Moon goes around Earth, and Earth goes around the Sun. The Sun, carrying the entire solar system with it, moves steadily around the center of our galaxy. It takes our solar system 200 million years to make one circle about the galaxy. That means that since the solar system was formed nearly 5 billion years ago, it has circled the galaxy 23 times. Some of the material in the outskirts of the original nebular cloud stayed small. This is especially so between the orbits of Mars and Jupiter. There may be as many as 100,000 small bodies called asteroids that are at least a mile across and circle the Sun. A few have been captured by planets and become small satellites. Those that move in closer to the Sun and even pass near Earth are known as meteoroids while they are in space, meteors as they enter Earth's atmosphere, and meteorites when they actually hit Earth's surface. This time-lapse photograph of a meteor shower shows meteors as vertical pinkish streaks, while stars make slightly curved trails. Astronomers have concluded that far beyond Pluto there exists a cloud called the Oort cloud that contains hundreds of billions of small lumps of ice left over from the formation of the solar system. We call these lumps of ice comets. The Oort cloud has never been seen, but it is possible that the comets extend outward for over 10,000 billion miles, 16,000 billion kilometers. Every once in a while, a comet drops toward the Sun and passes by the planets. The Sun's heat evaporates the comet ice. Clouds of trapped dust emerge and surround the comet, glittering in the sunlight. Solar wind, which is made of energetic particles shot out by the Sun, sweeps the dust around the comet into a luminous tail that always points away from the Sun. This gives a magnificent view of the comet from Earth. Our solar system works fine now, but it won't last forever. A nebular cloud contracted to form a solar nebula. A protosun and disk eventually took on the form of our solar system today. But in 5 billion years, the hydrogen at the Sun's center will run low. The Sun will expand, and the outer layers will cool and redden, turning it into a red giant. Finally, the Sun will not be able to have any kind of nuclear fusion at its center. It will collapse into a tiny white dwarf no bigger than the Earth, with cold, dead planets circling it. It doesn't seem likely that our Sun is the only star to have a family of planets. There are hundreds of billions of stars in our galaxy, and hundreds of billions of other galaxies. Some scientists think that most or even all of these stars have planets. In the last few years, we have found that some stars seem to be circled by clouds of small bits of matter. This disk around the star Beta Pictoris just might be a solar system. But even the nearest stars are so far away we can't actually detect any planets that may exist. Even Alpha Centauri, the nearest star to us, is nearly 25 trillion miles, 40 trillion kilometers away. Someday, with improved instruments, we will see just what is out there beyond our solar system, in our remote corner of the Milky Way. How did our sun come to be? According to scientists, about 5 billion years ago, a huge cloud of dust and gas swirled in the universe. Perhaps a star nearby exploded, and the gases driving out of this supernova caused the cloud to begin contracting. Its own gravity made it continue to contract, and it grew hotter and hotter as the gases became more and more compressed. Eventually, the center of the cloud became so hot that the material in it began to change. These reactions produced even more heat. Finally, the center of the cloud caught fire, and the sun was born. What might have happened at the center of the cloud to make it catch fire? Let's compare the sun to a hydrogen bomb. In a hydrogen bomb, intense heat develops. This forces atoms of hydrogen to smash together and fuse, forming helium. This fusion produces enormous amounts of energy. The sun is about 3/4 hydrogen. Its core is so hot that the hydrogen fuses into helium. This creates intense energies that slowly leak out of the surface as light and heat. The center of the sun is about 25 million degrees Fahrenheit, about 14 million degrees Celsius. The surface is over 10,000 degrees Fahrenheit, about 5,500 degrees Celsius. The heat energy on the surface is very active. These swirling waves show how the sun's surface rises and sinks. It seems to consist of granules of matter closely packed together. Each granule lives about 8 minutes and then is replaced, like bubbles in boiling water. These granules may look small, but on the average, each one is nearly 600 miles, 1,000 kilometers across. Scientists think that there are about 4 million granules on the sun's surface at any one time. Here and there, the hot gases of the sun expand and become cooler. These gases shine less brightly than hot ones, so some areas are dark. These are called sunspots. The number of sunspots varies. Some years there are 100, in others, 10. Normally, sunspots are seen as irregularly shaped holes. Some unusual shapes, such as spirals, can have diameters 6 times that of Earth. Areas around sunspots are a little hotter and have more active gases. Explosions near these spots, called flares, shine very brightly and give off a lot of energy. When the sun is particularly spotty, Earth is also a bit warmer. Dark ribbons of cooler gases between sunspots are called prominences. We can see them with special instruments. They lift off the sun's surface and erupt through the thin outer atmosphere called the corona. When viewed straight on, prominences look like dark filaments, but coming off the edge of the sun, they form graceful arches tens of thousands of miles high. Scientists believe prominences show active areas where flares will occur. This activity in the corona can be charted with a coronagraph. Large spikes or streamers of activity can be over 1 million miles long. All this activity on the sun's surface sends tiny electrically charged particles outward in all directions. This stream of particles is called the solar wind and travels at about 300 miles or 500 kilometers per second. These particles strike Earth's atmosphere, particularly near the North and South poles. Energy from the collision is released as light. As a result, the nights in the polar regions are lit by faint colored lights in streamers and curves. In the northern hemisphere, this light is called the aurora borealis. In the southern hemisphere, it is the aurora australis. Sometimes when the sun is very active, the auroras can be seen beyond the polar regions. Why do we need this powerful star? The sun provides light, heat, and energy. Without it, there would be no life on Earth. Imagine how relieved ancient people were when the sun rose each morning and brought light and warmth to their world. Many ancient peoples, like the Egyptians, worshipped the sun as a god. They felt the creation of the world was made possible by the power of the sun. This ancient belief was not far from the truth. Our sun, a middle-sized star, is just the right size. It not only produces enough energy for life, but also will survive for a total of 10 billion years. This gives the time needed for life to form. Within our solar system, this brilliant star is huge. The sun is about 108 times as wide as the Earth, represented by the white circle, and has almost 350,000 times the mass. In fact, the sun has almost 1,000 times the combined mass of all the planets, satellites, asteroids, and comets that circle it. This huge mass gives the sun a gravitational pull so strong that it holds all these objects in orbit around it. Our moon has helped us learn about the sun. Sometimes the moon moves directly between us and the sun, blocking the sun's entire body. This blocking, called a total solar eclipse, leaves the corona shining softly as a kind of halo around the moon. Total solar eclipses can last up to 7.5 minutes. Each year, there are from 2 to 5 partial eclipses. Since the moon's shadow falls over only a small part of Earth at a time, people in one area see a total solar eclipse only about once every 300 years. Most of the time, we use instruments to study the sun. Tracking stations are used to follow solar eclipses. And since 1931, we haven't had to wait for an eclipse to look directly at the sun. Scientists have used a coronagraph to cover the sun and study the corona. Spectroscopes are used to watch sunlight. This instrument spreads out in order of length the tiny waves that make up light. In a spectrogram, the white light portion of the spectrum is split into all its colors like a rainbow. Scientists also use an instrument called a spectroheliograph to study particular wavelengths of the sun. This tells them what elements like hydrogen and helium make up the sun. However, there is a lot about the sun that we cannot know from Earth. The atmosphere absorbs much of the sun's radiation before it reaches Earth. In order to study all the sun's radiation, we must observe it from outside our atmosphere. Since 1957, nations including the United States, Japan, the Soviet Union, West Germany, and India have built and launched special satellites for such studies. In 1973, Skylab carried human beings into space where the sun's radiation could be studied. Skylab discovered some regions in the sun's corona that were cool and had little gas in them. These regions are called coronal holes. They are believed to be the main outlet for the solar wind. We have learned how to harness some of the sun's energy for heating to help us conserve resources like coal and oil. Perhaps we could use a huge space mirror satellite to reflect the sun's light during nighttime blackouts. There is still a great deal to find out about the sun and how we can use it creatively on Earth. Scientists continue to study the sunspot cycle in order to learn more about what goes on deep inside the sun. Who knows what we might be able to do someday as we continue to unravel the mysteries of our star, the sun. To most of us, a comet is a hazy patch in the sky. From night to night, as it slowly moves among the stars, the comet gets brighter, but then it fades away. This hazy patch of light stretches out into a tail that always points away from the sun. The tail gets longer as the comet grows brighter, until sometimes it stretches far across the sky. But as the comet disappears, the tail shortens and fades as well. A tail is but one of many things people think of when they see a comet. People have imagined a comet as a woman's head with long hair streaming behind. In fact, the word comet comes from a Greek word meaning hair. Meteors, like comets, have fascinated people for centuries. Meteors look like stars that briefly move across the sky and then suddenly vanish. Any clear moonless night, especially after midnight, you can see such shooting stars. Sometimes you can see dozens in a single night. Meteors are usually quite dim, but sometimes they are bright and are called fireballs. In this artist's concept, a fireball briefly brightens the early morning sky. On Earth below, sky watchers have witnessed a brilliant shooting star. Meteors are not really stars, however. The word meteor comes from the Greek words meaning things in the air, and this is exactly what meteors are: shining objects streaking through Earth's atmosphere. If the matter that forms a meteor travels all the way to the ground without burning up, it strikes the Earth and becomes a meteorite. Very large meteorites have dug out craters on Earth, the Moon, Mars, and other worlds. In some ways, comets and certain kinds of meteors are related. Here's how this works. The haze of a comet contains countless particles of dust. Following the path of the comet, this dust scatters through space. Some of this dust is concentrated into large clumps. In this artist's rendering, clumps of such dust particles are pictured trailing along in the orbit of a burned-out comet. Earth may pass through such clumps. The dust particles then speed rapidly through Earth's atmosphere, and as a result of friction, the particles heat up, become white-hot, and glow. The result is a meteor shower. Comets have been seen throughout human history, but until recently they have always seemed to appear out of nowhere. In 1950, an astronomer, Jan Oort, pictured here on the left, figured out that there must be trillions of comets circling the Sun at a huge distance. This comet cloud, called the Oort cloud, consists of icy comets containing rocky dust. Some may even have rocky centers. The Oort cloud surrounds our solar system, orbiting the Sun far beyond Pluto. Sometimes a comet may be pulled at by a distant star, or two comets may collide, as illustrated here. A comet's motion may then slow, and the comet will fall toward the Sun. As it approaches the Sun, the ice warms and forms a dusty vapor, which is what we see from Earth. A dirty snowball, bits of rock and dust mixed into a ball of ice, is perhaps our best model of a comet. When the ice ball warms near the Sun, part of it turns to gas and carries the dust into space. But not all meteors are caused by comet dust. Many meteors are caused by tiny asteroids or asteroid-like objects made of rock and metal speeding through space. While they are in space, they are called meteoroids. Once meteoroids strike Earth's atmosphere and become white-hot, they are called meteors. Most meteors are tiny and heat entirely into vapor, but some are large enough so they don't completely burn up. Bits of them survive and strike Earth's surface as meteorites. In most places on Earth, unless you happen to see one hit the ground, you're not likely to find a meteorite. Most are too much like ordinary rocks. But in the Arctic and Antarctic regions, a piece of rock on top of the ice would just about have to be a meteorite. Some 7,000 meteorites like this one have been discovered in Antarctica since the 1960s. Reports of meteor sightings weren't always taken seriously. In 1833, however, Earth passed through a huge collection of tiny dust particles in space. It was the biggest meteor shower ever reported. Some people thought it was the end of the world. Reports of the shower got everyone thinking about meteors, and pretty soon it was clear that stones could fall from the sky. Like meteoroids, comets come in a variety of sizes and shapes. Some are quite large and spectacular. Large comets appeared in 1811, in 1861, in 1882, and in 1910. The comets that appeared in 1861 and in 1910 had tails that appeared to stretch halfway across the sky. This is the most famous comet of all, Halley's Comet, as it appeared in 1910. Since 1910, however, there have been few bright comets, none like the real giants of the century before. The truth is that hardly anyone living today has ever seen a really spectacular comet. After Isaac Newton worked out the law of gravity in 1687, his friend Edmund Halley became fascinated with comets. Halley became the first person to predict a comet's return. A comet in 1682 had crossed the sky, following the same path as comets in 1531 and 1607. This is a sketch of the comet's appearance in the 17th century. Using the law of gravity, Halley showed that what was thought to be three different comets was actually the same comet traveling around the Sun in a long orbit and returning about every 76 years. He predicted the comet would return in 1758, and it did. It has thus come to be known as Halley's Comet. Since then, it has returned in 1835, 1910, and 1986. This up-close view of Halley's Comet was shot in 1986 from the Giotto space probe. It shows the core of the comet as seen from only 16,000 miles, 26,000 kilometers away. Even in relatively recent times, people have thought that comets were a heavenly sign of coming war and disaster. This is a street scene in Paris in 1811 as a comet passes overhead. In 1910, it seemed that Earth would pass through the tail of Halley's Comet, and many people were afraid the world would come to an end. But nothing at all happened to Earth. Every time a comet moves about the Sun's heat changes it. Some of its icy material evaporates to form a cloud of dust and the tail. This material never returns to the comet. Over the years, the comet shrinks, and after returning many times, all its icy material is gone. The rocky core that remains may resemble little more than a meteoroid. If there is no rocky core, the comet vanishes altogether and leaves nothing but a cloud of dust. Astronomers have even seen comets plunge into the Sun. Taken in 1979, this picture shows how comet Howard Kuhlman Michaels raced toward the Sun. Only a cloud of dust and gas emerged from the other side. Earth has long been pelted by countless objects from space, most of them burning up harmlessly in our atmosphere as fiery meteors. Sometimes, however, a sizable meteoroid or comet hits the surface. On the young planet as pictured here, the atmosphere, oceans, and volcanic activity erased Earth's craters. On airless worlds like the Moon, however, the surface is still covered with craters that never fill in. Even more recent craters on Earth are usually filled in by the action of wind, water, and life. Yet this large crater in Arizona, where a meteoroid may have struck between 15,000 and 40,000 years ago, remains, evidence of the potential power of such impacts. Based on geological evidence, some scientists have suggested that a comet or meteorite impact some 65 million years ago may have created the disaster that signaled the beginning of the end for the dinosaurs. When Halley's Comet returned in 1986, it was met by Russian, Japanese, and European rocket probes that sent exciting information and pictures back to Earth. We now know, for example, that Halley was as dark as coal. Its surface ice had evaporated, but the solid dust remained, so it was a very dirty snowball. Halley's dust contained chemicals that have told us things about interstellar space and the early days of our solar system. A future comet mission, as depicted here, will place a space probe in orbit around a comet's nucleus in order to monitor changes as the comet circles the Sun. With more such comet encounters planned, scientists expect comets to act as probes themselves, carrying all sorts of news about the cosmos into our solar neighborhood. In 1801, scientists thought they had discovered a new planet between the orbits of Mars and Jupiter. They called it Ceres. It was smaller than any other planet, only about as wide as the country of France. Then a few years later, more objects were discovered in the same region that were even smaller than Ceres. They seemed like a pile of large rocks circling the Sun. Today we call these objects minor planets, or asteroids. They look more like flying mountains than planets. About 3,000 have been discovered, and there may be hundreds of thousands more. Most asteroids are very small, only a few miles across. And most have been found in between Jupiter and Mars. This area is called the asteroid belt. Mars is at the inner edge of the asteroid belt. Some asteroids might get trapped by Mars' gravity. The small moons of Mars could actually be trapped asteroids. The moons don't look at all like Mars. Mars is light in color and reddish. Its moons are dark, like many asteroids. Jupiter is at the outer edge of the asteroid belt. It has 16 moons, and all of these are probably captured asteroids. Here's an illustration of the asteroid belt. Jupiter, with its single thin ring, is on the right. There are also two clumps of asteroids in Jupiter's orbit. These are called the Trojan asteroids. The Trojan asteroids and Jupiter orbit the Sun in a very consistent formation. It is so steady that if you drew lines between the Sun, Jupiter, and the two groups of asteroids, you would have two equal triangles. Farther away in the outer reaches of the solar system, there might be thousands of asteroids. Saturn's outermost moon could be a captured asteroid. Pluto, the farthest known planet, and its moon are considered asteroids by some astronomers. Asteroids have very different shapes. This one, called Hector, might be two asteroids melded into one. Asteroids also behave in different ways. A few have long, thin orbits that take them relatively close to the Sun. Some asteroids crash into planets and cause craters like these on Mercury. Dozens, perhaps even hundreds of asteroids move past Earth. A few come so close they are called Earth grazers. In 1972, an asteroid fragment entered Earth's atmosphere over Idaho. It slipped through the atmosphere and back into space. Here is an aerial view of a crater in Arizona that is about 3/4 of a mile, or 1.2 kilometers across. This was caused around 50,000 years ago by an asteroid that did not return to outer space. It pounded into the land, leaving a huge hole in its wake. Prehistoric people may have sought iron from asteroids that hit the Earth. They used the iron for making tools. Small asteroids that enter the Earth's atmosphere are called meteors. A meteor is commonly known as a shooting star, yet it is not a star. It's just a small asteroid being burnt up as it falls toward Earth. Millions of meteors plunge toward our planet every day. The atmosphere shields us by burning up the meteors before they can land. This is one reason the Earth can sustain life. Someday, people might live on places besides the Earth. In colonies on Mars and the Moon. Astronauts from these space colonies will be able to explore the asteroids. These explorations will help us learn about the early days of the solar system and how the planets came to be. Asteroids might also be mined by people from space colonies. The arms of a mining craft would have to be very strong and flexible. Among the things asteroids would yield are iron, steel, oxygen, and soil. And who knows, by that time, maybe people won't need spacesuits. Some asteroids might even be hollowed out and converted into huge starships. On board will be thousands of people drifting outward, away from the sun forever, on a long, long journey to the distant stars.